Hello, my name is Hendrik van Antwerpen. Today I'll talk to you about how to derive language implementations from language specifications. This is joint work by Arjen Rouvoet, Casper, Bach, Poulsen, Robbert, Krebbers, Eelco, Visser and myself. Manually implementing languages is often a time-consuming and error-prone task. In an ideal world, we would not have to implement languages ourselves anymore. Instead, we write formal language specifications from which the language implementation is derived by tools such as language workbenches. Importantly, this moves the burden of proving correctness of the implementation from the individual languages to the language workbench. For some language aspects, this ideal is already reality. Language syntax is specified using context-free grammars from which parser implementations are derived by parser generators. For static semantics, that is for type checking and name resolution, this ideal has not yet been fully realized. The specification and implementation of name resolution, supporting all the features that we find in modern real-world languages, is a big challenge in realizing that ideal. In previous work, we introduced the static specification language, tailored to a high-level specification of name resolution. In this paper, we produce executable type checkers from these specifications. Getting from a specification to an implementation requires us to solve a scheduling problem. This scheduling problem is faced in some form by all type checker implementations. Consider, for example, this program consisting of an object O with a body containing two mutually recursive definitions F and G. Because the definitions are recursive, both the forward reference G and the backward reference F resolve correctly to the corresponding definition. To correctly resolve the references, the type checker needs to ensure that all definitions are known when checking each definition body. One common solution to achieve this is to first aggregate all binders and then check each body definition in the context of all collected binders. This is of course such a simple example that we might not think of it as solving a scheduling problem. But the name binding features that we find in real-world languages pose much harder versions of such scheduling problems. One can think of mutually recursive imports, nested modules and classes, or type member projections. In these cases, the necessary name binding information may come from different parts of the AST, and resolving names may depend on the resolution of other names or on the types of expressions. This introduces dependencies in the type checking problem that complicate both the specification and the scheduling of the implementation. Our goal is to solve the scheduling problem for the static specification language. In the rest of this talk, I will first introduce the specification language Statix and explain how it addresses the specification problem. Then I will discuss the scheduling problem for Statix, which generalizes the scheduling problem of specific languages. I'll explain the insights that we use to solve it so that we automatically obtain provably sound type checkers. What does a static specification look like? It consists of typing rules which are driven by a model of name binding, a scope graph. Typing rules assert and query this name binding model using a few built-in constructs provided by Statix. So let's take a look at an example of such a scope graph. The program on the left of the slide is an extended version of our earlier example. The object O now extends an object C, which contains a definition G. Note that the resolution of the reference G in O is unchanged. The local definition is preferred over the inherited one. The scope graph, depicted on the right, models the binding aspects of the program. It consists of nodes representing scopes and declarations and labeled edges describing their relation. The scope of object C is represented by the scope node SC. The declaration node SG', carrying data with the name and type, corresponds to the definition of G. The fact that SG' is a declaration in scope SC is indicated by the edge labeled with D for definition. Similarly, the object O has a scope SO with edges to the declarations of F and G. Object extension makes the definition from C reachable in O, which is modeled by the edge labeled E for extension between the scopes SO and SC. And finally, the scope SB corresponds to the body of the definition of F and is connected to the surrounding object scope by an edge labeled L for lexical parent. The edge labels, which can be freely chosen by the specification writer, are used to control name resolution. Names are resolved by finding path in the scope graph. This is expressed as queries in terms of reachability and disambiguation. The variable rule shown in the bottom left corner of the slide shows the query used to resolve variable references. We'll go over each aspect of the query separately. First, reachability, expressed as a regular expression over labels, determines which declarations are in scope. The given regular expression says that declarations from the lexical context are in scope, as well as declarations that are reachable via extension edges. When multiple declarations are reachable, disambiguation specifies which one is preferred and which one is shadowed, expressed as an order on path. In this example, disambiguation is specified as a lexicographical order on edge labels, which says that local declarations are preferred over declarations via lexical and extension edges. The last part of the query specifies that the query must unambiguously resolve to a single declaration with name F and type T. Let's look at what this means for the reference G in scope SB, shown in the dotted box in the scope graph. By the regular expression, there are two G declarations reachable in the graph, the one from O and the one from C. By the order on path, the definition in O is considered closer and is thus preferred. Therefore, according to this rule, the reference G will resolve to the declaration in SO. Now that we have an idea of how resolution works, how do Statix rules specify this scope graph model? The rules of a static specification are close to regular typing rules. However, they use special constructs to assert the structure of the scope graph. Let's first look at the rule for the body of the object and the relevant part of the graph. The conclusion of the rule has a scope reference S on the left, depicting the lexical context. The first premise asserts the existence of a fresh scope for the body, represented by the meta variable S prime using the nabla constraint. The second premise asserts the edge from the body scope S prime to the lexical scope S. The third premise simply specifies that the lexical scope of the definitions in the body is S prime. Importantly, we do not specify the inhabitants of the scope S prime here. Instead, the typing of the body can simply assert inhabitants in it. This can be seen in the rule for definitions, which checks the body expressions in the context of the given scope S and asserts a new declaration, which is added to S by asserting a definition edge. The mutually recursive nature of the definitions is achieved by checking the body expressions and asserting the declaration in the same scope F, S, which is shared by all definitions in the body. The advantage of Statix is that it enables you to specify many interesting name binding patterns in a style that remains close to traditional typing rules. With traditional typing rules, specifying these name binding patterns requires bookkeeping of environments to aggregate binders and encode reachability and disambiguation in the operators applied to these environments. In contrast, the Statix rules do not require explicit aggregation, and the rich structure of the scope graph model allows us to factor out reachability and disambiguation into separate resolution queries. This is achieved by having a model of binding that is independent of the typing rules, a uniform expressive resolution mechanism, and built-in constructs to generate the model. This makes Statix scale well to binding of real-world languages. As part of our evaluation, we modeled interesting name binding aspects of Java and Scala in Statix. On the slide you can see a small sample of what textual Statix specifications look like, and these specifications are one part of the paper's artifact. Now that we have seen the specification of binding in Statix, it's time to discuss how we derive an implementation from such a specification. Previous work defines a declarative semantics for Statix, given by a constraint satisfaction relation, which specifies when a scope graph model satisfies a given constraint. What was missing, what we develop in this paper, is an operational semantics that specifies how to go from a constraint to a model, if such a model exists. Putting the burden of proof with the language workbench, we want to prove that the operational semantics correctly implements the declarative semantics, thus proving a soundness theorem. The main challenge in developing a sound operational semantics for Statix was solving the scheduling problem for Statix. So what does this scheduling problem for Statix look like? We have already seen how names are resolved in a scope graph with the example of the reference G. The scheduling problem occurs because during type checking, the scope graph may not yet be completely constructed. Consider an intermediate state with the scope graph as shown on the slide, where the definition of G is not yet seen by the type checker, and the declaration is still missing from the scope graph. Trying to resolve the reference G in this state will give a different answer than resolving it in the final scope graph. Instead of resolving to the local definition, it resolves to the definition in the object C. However, this definition is shadowed by the definition of G in O once that one is added. We say that the answer to the query in this intermediate graph is unstable, as it differs from the answer in the final graph. Resolving G in this intermediate graph is therefore unsound. You may wonder if it's not possible to construct the model scope graph before doing any queries. The answer is unfortunately no. The reason is that scope graph construction may also depend on name resolution. For example, constructing the extension edge in our example requires resolving the object name C to determine the target scope of the edge. Therefore, we need a more fine-grained approach that interleaves construction and resolution while still guaranteeing stable query answers. When it comes to a query, we must know when to ask. So how did we achieve this fine-grained approach? The key to our approach are critical edges. Critical edges are those edges in the model graph that are relevant for the query, but that are missing in the intermediate graph. The presence of critical edges indicates that a query answer is unstable in an intermediate scope graph. On the slide, we see the same intermediate state we discussed before, where the declaration G is missing. It is shown in a different color to indicate that it is part of the model scope graph, but not of the intermediate graph. The variable rule is shown on the right for reference. The missing definition edge from SO to SG is relevant to the query, since it is allowed by reachability and leads to a matching declaration, and therefore it is a critical edge. Critical edges are precise characterization of whether a query will have a stable answer or not. But the problem is determining critical edges requires knowing the model scope graph, and therefore this idea cannot immediately be turned into an implementation. So how did we turn this idea into an operational semantics? The operational semantics is defined over a tuple of the current intermediate scope graph and the remaining constraint program. The main idea is to delay resolution of a query in the intermediate scope graph until we are sure there are no more critical edges. To achieve this without knowing the model beforehand, we have devised a way to determine this based on the remaining constraint program alone without doing any constraint solving. And to make this feasible in practice, we do two things. We over-approximate the critical edges, and we restrict aliasing of scope references for the purpose of scope graph construction using a type system based on scope ownership. This made a decidable operational semantics feasible. I cannot go further into the details here, but I encourage you to read the paper for that. With the operational semantics we developed, we get executable type checker implementations from Statix specifications. In the paper, we prove that the resulting type checkers are sound and also confluent. And we implemented this operational semantics in mini-Statix, which is a Haskell implementation. Using mini-Statix, we evaluated our approach by executing the Java and Scala specifications against a suite of tests. This evaluation shows that the approach indeed gives an implementation that correctly passes all the tests, and that the over-approximation of critical edges that we applied is still precise enough to support all the Java and Scala name binding patterns that we modeled. Mini-Statix, as well as the specifications and the test suites for the case studies, are all part of the paper artifact. To try it out and have some hands-on experience of Statix, go to the URLs on this slide and give it a go.